something? What do you mean? Like, what's in my hand right now? Nothing, right? No! On your hand right now are teeny particles of nitrogen, oxygen, and a bunch of other gases that we cutely call air. Man, that's an easy problem to solve. Just go to a flat region of empty space. Like, what's in my hand then? Nothing. No! Empty space isn't empty. Boy, you tripping. Nothing is something and empty isn't empty?
Shh, let me explain. It's said that in flat regions of empty space, tiny massless virtual particles appear in pairs of matter and antimatter for extremely tiny fractions of time, before immediately colliding with and annihilating each other. In regions outside the black holes, only particles with positive energies can exist. However, the space-time curvature inside a black hole is so extreme that the notions of time and space are reversed. This allows particles with negative energies to exist within the black holes. This is why the event of annihilation does not take place on the event horizon. Instead, the virtual particle with negative energy gets sucked into the black hole, where it can exist as a real particle, while the virtual particle with the positive energy is ejected into space, where once it gets far enough away in space and time, it becomes a real particle and can be seen by distant observers as radiation from the black hole. On the other hand, due to the addition of the negative mass to the black hole evaporates a very small fraction of its mass, comparable to the energy of the absorbed particle. And this keeps repeating itself until the black hole eventually completely dies, well, 10⁻70 years later. This phenomenon was discovered by and named after our favorite Simpsons character, Stephen Hawking, and is called Hawking's radiation.
Ah, I get it now.
No! Time to quantum everything. The quantum theory states that objects are both particles and waves at the same time, and the quantum field theory states that space-time is filled with quantum fields. These fields are where quantum waves with positive energy, matter, and negative energy, antimatter, propagate. However, due to quantum uncertainty, the frequency and hence the energy levels of these waves is unknown and said to fluctuate. It is these fluctuations in energy that we have come to call as our virtual particles. In a vacuum, the system of positive and negative waves is in equilibrium, with the virtual particles also annihilating each other. But what happens to these fields near a black hole? To explain this properly, we would need a theory of everything, which we just plain don't have yet. So let's try to work around it. Let's look at a null geodesic, a single path in space and time, with a single quantum field with various waves in systematic equilibrium that propagate at light speed. This path extends from infinite past to infinite future and passes through a black hole just the moment before it was formed, and hence being the last path through flat space without the black hole. According to Hawking's calculations, certain waves from the quantum field are scattered or deflected by the forming gravitational field, causing them to be nudged off the narrow escape path and lost inside the forming event horizon. With the loss of some of these waves, the original equilibrium of the system is disturbed, and the new resulting equilibrium can be viewed by external observers as a field full of particles. But these can only be seen by external observers, as an observer in free fall into the black hole will be accelerating at the same rate at which the lost waves are. Therefore, in his frame of reference, the lost waves still exist. Hence, the initial quantum equilibrium is still maintained, and the observer does not see any particles.